So welcome to the seminar, everybody. Today we have Bence from our own institute here, and he will talk about ring-theoretic infiniteness in reduced products of Banach algebras. Take it away.
Array? Yeah, okay.
Okay.
Yeah, so far this was totally unimportant, everything I said. Don't worry about it. You said this project came about, so it was one of those instances where my question was not completely retarded, and we managed to get some interesting work done with Matthew Dawes, who's from the University of Lancashire. So I have to tell you a bit of background. Are you kidding me?
Maybe it just needs to be clicked on the screen.
What?
Somehow, like, get focus onto the like.
Yeah. Okay. Manually. So just some overview definitions. So throughout this talk, when we are in an algebra and I'll say something is an idempotent, I literally just mean that it squares to itself. And there is a notion of equivalence, purely algebraic equivalence between idempotents, by which I mean that P and Q are equivalent if you find some elements A and B in the algebra, such that P is A times B and Q is B times A. Okay, and we say the two idempotents are orthogonal if PQ is 0 and QP is 0. So this is just the bare minimum definition that we will need. And of course, as you all know, this is a genuine equivalence relation on the set of idempotents in your algebra. For now, let me fix the unital algebra with a multiplicative identity, and I'll say that the algebra is Banach infinite or Dirac infinite or DF if whenever you have an idempotent which is equivalent to the multiplicative unit in the sense on the previous slide, then this is actually the identity, the multiplicative identity. And we say that it's Dedekind infinite or DI if it's not DF. This means just that you find some idempotent in your algebra, that it is algebraically equivalent to the unit, but it's not the unit. And it is your algebra is properly infinite or PI if you can find idempotents P and Q such that both of them are equivalent algebraically to the identity and they are orthogonal to each other. A few elementary observations. So what does it mean that something is DF, so Dedekind finite? It means that whenever you have elements A and B such that AB is 1, then BA is 1. So if something is a left invertible, it's also right invertible with the same inverse. And what does it mean that something is DI or directly infinite or Dedekind infinite? Well, you find some elements AB such that AB is 1, but BA is not 1. So, clearly, everything that's commutative is going to be DF. There's not much interesting going on there. But also, PI has the property properly infinite up there. This has very nice hereditary properties. Namely, if you have unital algebras A and B and your domain algebra is purely infinite, sorry, properly infinite. I'll keep, if I say purely infinite in this talk, I always mean properly infinite. Sorry, just if I mess it up. And if you have a homomorphism, which preserves the unit from A to B, then actually B is going to be properly infinite. What's the connection between these notions? Well, if something is properly infinite, it is also directly infinite. That's a very easy calculation. And there is at least one related notion for unital Banach algebras that I would like to mention throughout this talk, namely the notion of having stable rank 1. Of course, there's you can make sense of generalized stable rank in Banach algebras, but stable rank 1 for us will mean that the group of invertible elements in your Banach algebra is dense in the norm in A. So how does this relate to any of the previous notions? Well, I think it's an observation of Riefel from his 83 Proceedings of London Math Society paper that if you have a stable rank 1 Banach algebra, then you are actually Dedekind finite. So this means that if the group of invertible elements is dense in your algebra and you have something that's right invertible, that it is also left invertible. This is just a basically easy exercise using Carnot series. Okay, some examples now. Everything I will say, so all my algebras will involve the complex field. This is actually quite important. So very often I don't know how, even if things I'm going to say work for the real case at all. So some Banach algebras which have stable rank 1. CK spaces. If it is a compact, if K is a compact Hausdorff space such that its Hausdorff covering dimension is either 0 or 1. So the unit interval 0 is a perfectly good example. But here it's actually important. Here it's very important for this particular example that we are about the complex field. Otherwise, this is just dead wrong. Other examples: the reduced group C star algebra of the free group. This is Dijkema Rerdam. Then I think later Dijkema and Della push this further for more general groups, torsion-free non-elementary hyperbolic groups. And something that's not a C star algebra, but a Banach algebra, L1 of the integers with a convolution product. This also has stable rank 1, so the invertibles are dense. This is due to Dawson and Feinstein. Just this Dawson. It's not the co-author of my paper. This is Dawson. He's Dawes. Just so that there's nothing to do with the two persons have nothing to do with each other. And of course, matrices, they all have stable rank 1. And actually, no stable rank 1 is closed undertaking directed limits. So the car algebra, for example, will have stable rank 1. And this is due to Wigfeld probably. And something that's a bit closer to my own area of research. So this B of X means algebras of operators on a Banach space X. And this is somewhat surprising, but algebras of operators on Banach spaces can have stable rank 1, provided that the underlying Banach space is a bit weird, meaning hereditarily indecomposable. It's a rather technical notion, but those are weird Banach spaces, so not your old LP spaces, and usually not, there's no CK spaces. So these are quite weird Banach spaces which satisfy this. Now, okay, so I said that stable rank 1 implies direct finiteness, or Dedekind finiteness. So let me give some examples which are non-trivial in the sense that even though they are Dedekind finite, they do not have stable rank 1. Again, CK spaces provided that the covering dimension of the underlying compact Hausdorff space is greater than or equal to 2. So for example, unit disk. Wigfeld actually characterized the stable rank of CK spaces in this aforementioned paper already. So if you're interested in the details, it started at the very beginning of that. Now also L1 Banach algebras over commutative constellative monoids, which are not groups, will also have this property that they are Dedekind finite but do not have stable rank 1. It's a result of Tomek Kani and Shimon Draga. And something that was my own work, you can also have examples among algebras of operators on Banach spaces. If, for example, you take a Banach space, this Banach space of Matthew Tarbart, who constructed an indecomposable but not hereditarily indecomposable Banach space, which has additional weird properties, this will do the job for you. This result here builds on the one above, on this one actually.
So just quick question, do you have a concept of a stable DF or not? It's basically a concept of a stable finite exists
yeah, I mean, you can make sense of stable finiteness. So yeah, I mean, so if you take, so just imagine there's any Banach space here, then if you take any, and this has stable rank 1, sorry, this algebra, then if you take any matrix algebra of that will have stable rank 1 as well. So continue. So I also said that proper infinite implies Dedekind infiniteness. So let me give some examples which are Dedekind infinite or not properly infinite. Again, L1 of certain monoid, namely, for example, the bicyclic or bicyclic monoid. This is good. So this is not properly infinite, but it is Dedekind infinite. Big L1 of the affine group of the complex numbers. This is due to Yamon choice. So this is not MD choice. This is not that choice. It's a different choice. And again, algebras of operators on Banach spaces also have this property. Certain Banach spaces. So for example, you take the Peace-James space, that works, or you take continuous functions on the ordinary interval 0, omega 1. This will also work. And okay, so properly infinite Banach algebras, what examples do we have? Again, here of the form B of X, I apologize, I'm a B of X guy, as you obviously see. So all the canonical Banach spaces you could think of, they have this. You take them and you take the algebras of operators, it will have this property. So if you take small LP spaces or big LP spaces or nice CK spaces, then this is always this. Sorry, that's weird. This is properly infinite. Something that's a bit more obscure. Okay, so let me just. So you can take L1 like Banach algebras as well. So as not to explain here. So take the second Kunz semigroup. This is C-star algebra. This is not your Kunz semigroup. It's not the one which is this TLM Gardaya business. This has nothing to do with it. This is also called the polycyclic monoid. So this is a different semigroup. It satisfies the Kunz relations. What the O2 Kunz algebra does is the same semigroup. It's a semigroup with 0 elements, with a 0 element, which is denoted by this diamond. And how you actually construct this, what does that weird hash thing mean there? So this, you take L1 of this set. This is a perfectly legitimate Banach space. You want to put a product into it, which is this hash thing. And how you do this is that you realize that as Banach spaces, this one is isomorphic, actually isometrically to this one. So this is just L1 on the actual semigroup, and then you quotient with an ideal, namely you take the Dirac at the 0 element, and you take the one-dimensional ideal that it generates. And as Banach spaces, these are isomorphic, so you just pull back the product. There is another way of realizing this. If you know the cone algebra, then this is just an L1 completion of the cone algebra. I won't be talking about this more today, but hopefully at some point later. So okay, how can I make this upstairs disappear? Cannot? Okay, so the title says, so there are all these C-star algebraists are probably more familiar with the C-star algebraic versions of these definitions I just told, right? So how about that? So what happens then? So in C-star algebras, of course, we have projections, which are idempotents, which are self-adjoint. And of course, we have Murray-von-Neumann equivalence in C-star algebras, meaning what I wrote here, that you find some element V such that P is V star V and Q is V star. And orthogonality means that P and Q, if you multiply them, it gives you 0. So, okay, some easy observations again that you very well know. Murray-von-Neumann equivalence is an equivalence on the set of projections in C-star algebra. And here in this thing, this V that implements the equivalence, this is of course a partial isometry in your C-star algebra. And here, of course, I didn't say Q and P equals 0 because that's automatic. So usually how you define these notions that I just said, these purely algebraic ones in C-star algebras is as follows. So you fix some unit of C-star algebra with a multiplicative identity, and then you say that it's Dedekind finite again, DF, if whenever you have a projection, which is Murray-von-Neumann equivalent to the identity, then it is the identity. And it's Dedekind infinite if it's not Dedekind finite, so there is a projection which is equivalent but not equal to the identity. And lastly, it is properly infinite if you find projections such that both of them are Murray-von-Neumann equivalent to the identity and they are orthogonal to each other. So, but of course, the purely algebraic definition makes sense for C-star algebras as well. So what do you do? Which one do you pick? And it turns out that it's totally doesn't matter because they are completely equivalent to each other. So I couldn't find one reference proving this, but I'm sure there are many. But for example, in Dale's book, these results are scattered through. So it turns out that, for example, if you have a C-star algebra, which is Dedekind finite as an algebra, then it is Dedekind finite as a C-star algebra and vice versa. And the same thing with proper infiniteness. So these notions, these algebraic and C-star notions are completely equivalent to each other. Just a quick word about why this is. Well, one of the ingredients when you try to prove a result like this here is that whenever you have an idempotent in a C-star algebra, you can always find a projection which is algebraically equivalent to it, and it satisfies these relations in addition, actually, so it's a bit stronger than what I say here. And also, if you have two projections, so not idempotence projections, they are algebraically equivalent to each other if and only if they are Murray-von-Neumann equivalent. So there's nothing particularly interesting there. So what this title says, I think, is massive Banach algebra constructions. We are slowly putting ingredients together. Just let me remind everyone what ultra products and ultra powers and the asymptotic sequence algebra is. So let me just fix a sequence of unital Banach algebras, the ANs. You can take the L infinity of these ANs, which is just the bounded sequences. Each term belongs to, each small AN belongs to the capital ANs, and of course you require that the norms of these are uniformly bounded. The C0 sum of these algebras is those elements in the Cartesian product such that if you take the norms and the limits of the element, then that's 0. And lastly, there is this funny CU AN, where U is a free ultrafilter on the natural numbers. These are those elements from above here, such that in the ultra limit, these go to 0. So why is the L infinity here but not here? Well, because this is automatically a subset of this one, but if I would just put the Cartesian product here, this of course wouldn't be true. That's just a technicality, but just it's asymmetric and it's not doesn't
Just an elementary question, what's in bullshit?
ultra limit. Okay. So we'll not talk about ultra limits in this talk. Actually, yeah, let me, because it's actually I will go just with the easier construction in this talk, and then let me come back to this at the end. I'm sorry, just it's actually this is why I will go actually with this construction throughout the whole talk, and everything will work in the same way. So okay, so this L infinity is a perfectly legitimate Banach algebra, unital Banach algebra, in the pointwise operations, and then you put, of course, the subnorm on it. And oh my, that's not good.
Yeah. Click on the chat.
Yeah. So where is the okay, thanks. Yeah. That's the obvious thing, right? Yeah. So the C0 is a close two-sided ideal in L infinity, and also the CU that I didn't define, apologies. This is also close two-sided ideal, and actually this C0 is properly contained always in this guy. Okay. So I'm coining this notion, asymptotic sequence algebra. This is, I think, originally Ilias Farah's definition. The asymptotic sequence algebra is this object, this L infinity quotiented by this C0. And of course, the ultra product is L infinity quotiented by this other ideal. And for the purposes of this talk, I will actually, all the results I'm going to tell you will be about the asymptotic sequence algebra, but everything I tell you also works for the ultra products. The techniques are literally the same. So these guys are both unital Banach algebras. And yeah, the pi and pi will denote the quotient maps. And the norms on these guys, these quotients, can be realized in a rather concrete way. So in the asymptotic sequence algebra, it's the lim sup of the norm of the elements. And in the ultra product, it's actually just the limit along the ultra filter here. So typically these, although the construction is similar, these algebras can be very, very different. Typically, the asymptotic sequence algebra is a much larger object than this one. What do I mean by that? If you take the sequence to be the complex numbers, then the asymptotic sequence algebra of the complex numbers is just L infinity mod C0. So the continuous functions on the stone check compactification. But on the other hand, actually the ultra product of these objects will be just the complex numbers. So these are rather, one of them is much bigger than the other one. For the purposes of this talk from this ring theoretical infiniteness business, they behave the same.
No, sorry, is it beta n or is it the corona, like beta n minus n?
Sorry?
Sorry, is on the Asymptotic, is that the same as the conduced functions on the
Corona.
beta? That's on the corona, so it's
Yeah.
beta n minus.
Yeah.
Yeah.
Okay, so as I said, everything I was saying is talk will be about the asymptotic sequence algebra. But both the examples and the counterexamples I'm going to present, they work for both. And actually, you could, if you know stuff about reduced products, all the results that I'm going to say, they also work for reduced products. So the reduced product is basically a more general notion than an ultra product. Sometimes you care about these things. So you, instead of an ultra filter, you just take a filter and you take these constructions like that. Both as the asymptotic sequence algebra and the ultra product is actually just a special case of this more general one. So what's the aim of this talk? It's basically inspired by the C-star algebraic results, is to classify when the asymptotic sequence algebra has any of the corresponding infiniteness conditions in terms of the underlying algebras As. So just a quick reminder, what was the Banach finite? That's when you have an idempotent in your algebra. Sorry, that's when for any idempotent in your algebra, it's equivalent to the identity if and only if it is the identity. And the first result is basically what we did with math, is that whenever you have a sequence of Banach algebras, each of which is directly the finite, then the asymptotic sequence algebra will be directly finite. This is not so complicated to prove. I hope to give some details on this later. But the converse, surprisingly, is false, or maybe not so surprisingly, but for C-star algebras, the converse is true. I will say a word about that later. So the converse is false because you can actually construct a sequence of Dedekind infinite Banach algebras such that the asymptotic sequence algebra will be Dedekind finite. Yeah, we will see about that. But in certain instances, the converse is true. So in certain cases, the converse of this theorem will be true. However, basically the bottom line is that it works when you have nice norm control. I don't want to give the specific quantitative details for that because it's very non-illuminating, but here are two examples when the converse is true. So suppose you have a sequence of unital Banach algebras such that this object, the asymptotic sequence algebra, is directly finite. And suppose you are in one of the two cases. Either you are the constant sequence, so it's just you just have one Banach algebra and you take the asymptotic sequence algebra of that, or all your Banach algebras are actually C-star algebras. Then it turns out that provided that this big object, the asymptotic sequence algebra, is DF, then co-finitely many of the underlying algebras from your sequence will be directly finite. So that's again due to some fairly universal fact that you have very nice norm control in these cases. So the C-star case is, I think it's a super standard thing. Would struggle to find explicit reference for this. I think there are these papers which I will show at the end of Martino Lupini and Ilias Farah and Sherman. I think in those it's scattered through. They use continuous model theoretic results to present these proofs, but yeah, you can read on other proofs as well. Okay, proper infiniteness. I just want to say quickly something about this because the situation is completely reversed. So there, what happens is that whenever the asymptotic sequence algebra is properly infinite, then no matter how weird these things may or may not be, then always from your underlying sequence cofinitely many will be properly infinite. The converse is false again. So it can happen that you have a sequence of properly infinite Banach algebras, but this asymptotic sequential algebra will not be properly infinite. Yeah, these I will not talk more about proper infiniteness, I think, today, but because the DF, I will show some details of the proof of the direct infinite case, and actually the proofs are here similar, but just a bit more technical, and it's harder to keep track of things, but in the same spirit. So, but again, here the same thing happens. If you have nice strong control, then the converses are true. So C-star algebras, it's an if and only if statement, or if you actually just look at one Banach algebra, then this is again an if and only if statement. And again, the C-star case is well known for sure. Okay, so I mentioned this stable rank one thing. So stable rank again just means that the group of invariables is dense in your algebra. And here what we did with math, so here we didn't look at the sequence. So here we could only say anything about this when we just look at one single Banach algebra. So here, if the result is that if you know that the asymptotic sequence algebra, or Corona in this case actually, has stable rank 1, then your underlying algebra must have stable rank 1. This is actually rather easy to prove. You can prove a more quantitative version of this actually. But the converse is false, like very false. So even if you take a super easy, nice, well-behaved Banach algebra, L1 of the integers with a convolution product, then actually this has stable rank 1, but the asymptotic sequence algebra does not. Some fun facts that the proposition is sort of completely elementary to use in the sense that you don't need to rely on any technology. The counterexample, on the other hand, this uses a lot of hard and weird theorems, even from group theory. So it's a bit, and I have no idea if there is an easier way of doing it. That's the thing. And again, stable rank 1 for C-star algebras, it's an if and only if statement. This has stable rank 1 if and only if the Corona asymptotic sequence algebra has stable rank 1. This one I found in a paper of Farah and Erdogan, and they're using model theoretic methods, continuous model theoretic methods to prove this, I think. Right, so how much time do I have? Sorry.
25 minutes.
25 minutes, yeah, okay. So let me try to give you, so how do these proofs work? Just let me give you some detail. So this is the statement I would like to prove. This is the easiest one, but the methods are sort of already present there. So I would like to prove that whenever your sequence is directly infinite, then this asymptotic sequence algebra will be directly infinite. Some of the ingredients for the proof. The first one is a super elementary one that everybody knows, but it's very important, namely that in a Banach algebra, in a unital one, if you have an idempotent which has norm strictly less than 1, then it's 0. Okay, so this is trivial. Another one is a bit less trivial. This is sometimes called this approximate idempotent lemma. I'm not sure. I think some version of this is in Blackadar's book, the K-theory book, but I'm not completely sure. Anyways, the result is here that suppose you have an element in a Banach algebra which is almost an idempotent in the sense that the norm of the square to this element is less than 1/4. Then it turns out that you can find a genuine idempotent such that this is close to your original element A, and this closeness is controlled by some function, some nice function that I will show you in a moment. Moreover, whatever your element A commuted with, P will commute with it as well. So what is this control here? So this thing, the point is that this control only depends on this norm and the norm of A itself. This function f has some pleasant properties. Yeah, so this is just some monotone increasing non-negative continuous function from this interval to the reals. And yeah, you can make sense of this for each parameter m, and it has this property that fm is dominated by fn whenever n is greater than m. So now we basically set up to give the proof. It's worth breaking into several steps. The step one is actually you want to show something fairly natural looking, namely that you can lift idempotents from here, from the asymptotic sequence algebra to idempotents in the L infinity. So from the quotient, you lift them up. How do you do that? So pick some idempotent, choose some representative, let it be capital X and with accents. So because this is an idempotent, we have the property that actually pi of x squared is pi x, which is just the same as saying that x minus x squared belongs to the C0 sum of the ANs. So now let me just put these new n's to denote the norms of these guys. And because of this property, we know that this sequence goes to 0. In particular, they are all smaller than 1/8 from a certain index. And now we want to hit it with this approximate idempotent lemma. So we choose idempotents Pn primes, which are close to the xn's, like this close. So this is this omega n is just the norm here. Sorry, mu n's are the norms. And you can bound this further because of this property up here. Yeah. With the norm of the representatives, and then just using again that this is monotone increasing, you can bound this by this rather nice constant. And from continuity, you actually get that this sequence must also converge to 0, which means exactly that, sorry, which implies that this guy goes to 0 from an index. So. Now we just want to set your idempotents Pn's if they are Pn primes, if Pn's are sufficiently big and 0 otherwise, and then you want to basically later collect these Pn's into a big vector in L infinity of ANs. So you need to bound them first to see that you can do this. I'm using the bounds on the previous slide. We bounded this with this term, and this is just, of course, this is the sup norm of these guys. So you can indeed form this capital P out of these Pn's, and this will be a legit idempotent up here. Now, basically, we need to show that, okay, this represents the same idempotent that we had in the asymptotic sequence algebra. So this goes to the quotient, this not this pi. And this holds because we established this already. The previous slide. Now we can move on to step 2. We can now show that if P was such that it was equivalent to the identity to begin with, then actually we can, by just the very definition of the equivalence, find A and B in the asymptotic sequence algebra such that they implement this equivalence. Then you represent again these small a and small b with sequences. And yeah, you just write out what these things mean. Sorry, you write out what these things mean. They mean exactly this. And then choose a sufficiently small delta, whatever, just depending the norms on the representatives A and B. It's not particularly important, but this delta is of course less than 1. You choose sufficiently large indices such that in this previous slide, what you had here, oh, sorry, what you had here, because of these, you will have all these guys smaller than your delta. And then what you do is you define these UNs to be the product of AN and BN. And because this delta was less than 1 by the Karl-Neumann series, this means that these UNs, these A and BNs, these are invertible. And in fact, their distance to this one n is the unit in the algebra an. This is controlled by this quantity. This is just Kalman series. There's nothing interesting here. And then what you do is you define qn's to be, so you basically you sandwich the inverse of these un's with bn and an, and it's immediate because of its definition that this would be an idempotent equivalent to the unit in your algebra an. But recall that by the very assumption, these an's were Banach finite, so if they are equivalent, these are all the identity from an index one. So this everything we did there worked from a sufficiently large index. What we need to show that this P that we started with, which was equivalent to the identity in the quotient in the asymptotic sequence algebra, this is indeed the identity, which means exactly showing this. But if you have an idempotent, actually, I didn't say this, but of course, if you have an idempotent P, then identity minus idempotent is also an idempotent. So it's actually enough to prove that from some index on, so eventually these guys have no less than equal, strictly less than one, sorry. This is by this very trivial fact I said in the beginning. If you have an idempotent, you don't strictly less than one, then it's zero. So this is enough to prove this. I mean, it makes sense that you look for something like this given the quantitative bounds you have, so it's not something unexpected, right? So yeah, we move to, of course, from an index on. Again, these things hold by the previous relations we had above. And then, so the Pn primes was something this approximate idempotent lemma gave you, and the Pn by the very definitions, these are the same from this index on, and also this holds because this case is a sufficiently large index, and we established that by detecting finiteness we have equivalence here, so we must have actually equality here, genuine equality. So actually you do a series of retarded bounds with the triangle inequality. So this one n is the qn because of this pn is the pn prime because of this. I plug in the definition of the qn's. You do the triangle inequality, you add this and subtract this, and add this and subtract this, and we have bounds of these things above. Yeah, and here you take the bn and the an out, you have a unit, so you can do that. And we had control of this because of the Kalman series, basically. So you have exactly the bound that you wanted, because this is exactly going to be less than one. That's how you set the whole thing up. But this is what you wanted to show. You have an idempotent, this guy, this 1n minus pn, which has no strictly less than 1. So this idempotent must be 0, which exactly means that this identity must be equal to pn. So this is how you prove a thing like this. This is the generate method. This worked for the DF case when you do the pure properly infinite proof. The methods are very similar, but it's a bit longer and it's a bit more fiddly, but the same ideas work. Basically, why you do that proof? You also do that when you have equivalent idempotents in the asymptotic sequence algebra. You can leave them to equivalent idempotents upstairs. So why is the converse not true? I said that the converse of this theorem is not true for Banach algebras. Why is it not true? What goes wrong? The thing is that in Banach algebras, idempotents can have arbitrarily big norms. Why? So here is an example. This is a bit, I'm cheating a little bit because this is not the unit of Banach algebra. If you take L1 of the naturals with the pointwise product, this is of course not a unit of one, you can unitize if you want. So with the pointwise product, this is perfectly matching Banach algebra, and here if you define Pn to be just this sequence, so it has n ones and the rest is 0, the pointwise product, this is an idempotent, but it actually has norm n, right? So if you try to form a sequence out of these Pn's, this will not be bounded, of course, so it will not be an element of this Banach algebra. So that's the foolproof of the problem, that you may not have norm controls when you try to collect your idempotents together.
I mean, the these two algebras too, both could have arbitrarily large norms. The projections will all be norm one,
But that's the thing, you can work always with projections, because so that's what I tried to establish in these early slides. Sorry, maybe I was a bit rushed through that. Direct infiniteness and these things, you can, the definition is equivalent to saying them with projections. And then when you lift and to collect these together, they all have norm one. So in the supremum norm, they will also have, yeah, so. But that's exactly, thanks for the observation. That's exactly why it works for C-star algebras, these proofs. Yeah, so about the counter example that we gave. So I said that you can find a sequence of directly infinite Banach algebras such that this asymptotic sequence algebra or corona will be directly finite. I just want to tell you some ingredients of the proof. So the construction relies on Banach algebras of the form like this: L1 over some set I. This is a just let me say it formally. It's easier probably. So you have a non-empty set I. You have some function from I to interval 0 infinity, and then you consider all the functions from the interval to the complex numbers such that this holds. Its weighted sum converges. This is of course a Banach space with this norm. And you can realize it as the closed linear span of the Diracs. So it's meaningful to write elements in this form because it converges in this norm. So bear in mind that the norm has these weights, kind of weights in it. Didn't define what a weight is yet, but so when you have a monoid instead of just a set I and S, then a function like this is a weight if it satisfies this submultiplicativity condition and it maps the unit of the monoid into 1. And then the convolution product on this Banach space that we defined above is defined like that. So this is really, it's nothing tricky here. This is the convolution product you all know and love. And this is with this product, this is a perfectly sensible unit of Banach algebra, right? So we know that in Banach algebras, non-trivial idempotents, meaning non-zero idempotents, all have norm at least 1. But actually, in these Banach algebras, you can say something better. In these weighted L1 Banach algebras, you can do slightly better. Namely, that if you have any monoid with a unit S and you have a weight on S, and you have a non-zero idempotent, which is also not the identity, then actually in this norm, you can bound the norm of your idempotent from below by this quantity. So you take the infima of the weights, where these S's run through your monoid except the multiplicative unit, and then you need to halve it. So this means that if you put weird enough weights on some monoid, you can have actually these idempotents can indeed have very large norms. For the explicit counter example that I mentioned that we have, we use the bicyclic monoid, bicyclic or bicyclic? Which side of the Atlantic, I guess. Cyclic, bicyclic. Yeah. Mission is Cambridge education, so. So we use the bicyclic monoid, which is the free monoid generated by two elements, P and Q, subject to this single relation that P and Q is the identity. So it's usually written like this. Yeah, this is really the last slide. What you do is you define your weights on the bicyclic monoid as such. That's really simple, really. It's one when your S, your element, is the identity, and it's N everywhere else. And then you consider this sequence. These are the Banach algebras we're looking at. So they're all L1 Banach algebras on the bicyclic monoid, but with this weight. So it's just a weight that varies. And from this, you obtain that all these guys are Dedekind infinite. But actually, the asymptotic sequence algebra is going to be Dedekind finite. Now here I'm brushing a lot under the carpet. So where the work is done is here actually. This is where yeah, it's just some tedious calculations. And thanks very much for your attention. Yeah, one thing I use these references a lot, these works of Fahrenheit, Sherman. These are the sources where I found all the C-star algebraic proofs. They use very continuous model theoretic arguments most of the time. Basically, we are not using in our paper here any continuous model theory, but we mentioned certain things, how you would possibly be able to prove the positive results with the metric Walsh theorem for ultraproducts. But actually, it's a bit of a cheating because all you do is just pushing the problem elsewhere. So you're not actually using much continuous model theory because, Walsh theorem after all is induction. So it's not. So you can't. It's not a universal tool that solves your problem, but there are connections to continuous model theory. And one thing I didn't talk about today is there's another ring-theoretic property which is related to this, namely pure infiniteness, or C-star algebra is called purely infinite and simple. That's we didn't consider it in this paper, so what I talked about today, but actually it turns out that that's also worth looking at, because it turns out that there's a very, very natural Banach algebra which is purely infinite and simple, but actually there's no ultra power of it which is going to be even simple, let alone purely infinite and simple. And this algebra is very much like the classical Kunz algebras. Basically, it's a leave-it algebra, just with a different completion. Yeah, thank you, really. Thanks very much for your attention and questions.
Do you have any questions?
So just one question. Does anyone try to define a stable rank rather than a stable rank one?
Yeah, Riefel did. So Riefel's original paper from '83, he defined stable rank for all Banach algebras, or yes, and it's not depending on any C-star structure.
Okay, sure. Then that theorem that you prove for a stable rank, it might be true for a stable rank N.
Yeah, to be honest, I haven't looked at this. Yeah, thanks. I haven't looked at this. Yeah, thank you.
So, do you know that, for example, the stable rank of the algebra is something related? Because for C of X is related to the covariance.
Yeah.
I wonder about the algebra.
Ooh, I think Riefel did that. See, he determined, but unfortunately, I do not know the stable rank of this code, but it's certainly known, and I think it is Riefel.
And perhaps something about the cross product?
Oh, I haven't looked at any. So the cross products.
When, for example, every one of N or S or whatever you define has some df property or whatever. So, and then can you say something about the cross product of those things? Like, of course, in general, you cannot say anything, but maybe if you put some assumption on it.
I do not know. I don't know.
Thank you very much.
Thank you.
Other questions?
So yeah, so then you mentioned Walsh's theorem. I thought that was like the major advantage of the ultra products over the asymptotic sequence algebra, whatever, is that you have the Walsh's theorem for the ultra products, but not for the reduced products or the asymptotic sequence. So, but you also mentioned at the end you're saying that sometimes you can use Walsh's theorem even for your results, which are about the asymptotic sequence algebra.
You're completely right. So then it's wrong phrasing. So for the asymptotic sequence algebra, what's the equivalent of Walsh? It's the Pfefferman-Ward theorem, right? The metric Pfefferman-Ward, we couldn't make it work for the asymptotic sequence algebra. So the Walsh theorem, the metric Walsh theorem, we can only use it to deduce the results about the ultra products and the ultra powers.
No.
The ultra products.
So what's the Pfefferman-Ward theorem? I've heard of it, but I can't remember what it is.
It's the metric version of the, it's about analytic. So you can take specific filters, but for my life, I don't know what. So like analytic filters, I think, Vieshwav, do you know what it's sides result?
The original Vox theory was.
You do, okay.
But this is a bit more simple.
What's the original plot here? Yeah.
So it's sides result, this metric Pfefferman-Ward, and it's very technical, the condition. So.
And that applies to also asymptotic sequence algebras?
No, we couldn't make it work. Our referee actually for the paper suggested it, and we made like very concrete suggestion how we might make it work, but actually it broke at a certain point when we worked out the details. Turns out that it may be very well be that you just need to do something smarter, but we couldn't make it at least how the Walsh theorem worked. That's fairly simple. For the Pfefferman, thought you should be able to do something much more sophisticated. And given how elementary our proof is actually, so I didn't use any sledgehammers. It felt like a sledgehammer.
Thanks.
Yeah.
Yeah, just out of curiosity, during this work, did you manage to find the characterization for theorem 1 in the Banach?
Yes. Or yes, there is, but it's not very natural. I can write the precise statement, but it's yeah. Do you want me to show you the?
Yeah, I mean just what's
So the problem is so you have a fixed Banach algebra, and then the asymptotic sequence algebra. You want to determine when is an if and only if connection between still asymptotic sequence algebra having stable rank 1 and the Banach algebra, and it relies on the existence of some function, which gives you nice norm controls, but this function is not very explicit.
okay.
So it's an existence result, but it's not very constructive actually. You obtain continuous functions, which gives nice norm controls on the implementing invertible elements and the inverses, but it's not a constructive.
Because usually, I mean, why do we study this asymptotic algebra? Is it easier to somehow prove this one as the right one? Or
My motivation completely came from the fact that C-star people use it in Banach algebras. Unfortunately, I haven't seen many places where the asymptotic sequence algebra was used, I have to admit. that this was a bit of a, well, so in Banach algebras, I don't know if it actually helps you proving that some underlying object has as a stable rank one is easier than doing the asymptotic sequence algebra. I've never seen that used.
More elementary question, but
Just turn it off.
so more elementary questions. Well, at the start, you look at where the line equivalence in Banach algebras. So when I start to think about K-theory, and does the K-theory for Banach algebras may have very different here? There's significant differences between them.
Yeah, Banach algebras can have weird K-theory already. Already, if you look at the very restrictive class of Banach algebras, which are a form of bounded linear operators on Banach spaces, they can have already weird K-theory. So if you take one of these weird Banach spaces, these hereditary indecomposable Banach spaces owned by Gowers and Moray, they already have quite weird K-theory. But you have the 6 exact sequence and these things you have. So
fundamental results.
the fundamental, yes, both periodicity and these things they have.
Things that you get.
Yes. It's but it's hard to find, for example, a good resource for reading up on these things. Moray has some notes which are like somewhere circulating on the internet.
And further questions? I have actually just a quick question. Before you put up the slide, I was wondering if you had a purely infinite notion. And of course, now I see that that's.
Yeah, and then let me just write what purely infinite means for me. So A is, so A, this is just a unit of algebra. Then A is purely infinite. So it's in algebra, so it's not a division algebra. For every zero and some B and C in your algebra such that we are going to. This is algebraic, a purely infinite. So I just said purely infinite, but it of course immediately implies that your algebra is going to be simple, and it gives back the C star. It's equivalent to the many C star algebraic definitions of purely infinite and simple. But this is the one that you can sort of easy to make sense of in a Banach algebraic environment. And yeah, so this result is about that. Basically, there. Okay, I can spoil it. There, the example of this Kunst-like Banach algebra is that I mentioned in the beginning that you can take these polycyclic groups or second Kunst semi-groups, and then you remove the zero element. Let me just put 0, and you can take the L1 of this as a Banach space. You put this weird product on it, and you can take a further quotient of this by an ideal, which is generated by. Okay, it's basically an idempotent which generates it. This whole object it's the Leavitt algebra, the L2 Leavitt algebra closed up in the L1 norm, in the sequence norm, the norm of absolutely convergent sequences. If you take this guy, this will be purely infinite and simple, but and this is even a Banach star algebra, there's a very nice star operation, but there's no, you take an ultra power of this, it's never going, it's not even simple. Never mind purely infinite and simple. I hope maybe I can give more details at some point.
Okay, yeah, maybe that's a good idea. Is there any sort of like self-absorbing properties?
Ooh, I do not know. There may be. So Hannes Steele already asked these questions, and I'm staring at. Problem is with tensoring always in Banach algebras, right? That there are many. It's not even clear which tensor notion you should look at. Which one would be the right one? Projective, injective, some other tensor yeah.
And I was going to ask about tensoring. Like, if you tensor with this guy, does this give you another notion of pure infiniteness that's weak or stronger than you were?
So that's the thing. We already don't know which one should be the right tensor. I don't know. Sorry, I don't know. Maybe Matt knows, but I don't even know which should be the right notion of which tensor product we should look at.
Any other questions? If not, let's thank the speaker again. Why did we actually talk on Friday? 4 o'clock Friday.